this lab, we focus on harmonic motion, which is the motion that repeats in cycles in its predictable way. Some examples may include a spring and oscillating up and down, a circular motion like a merry-go-round. This motion can be described using sine and cosine functions. In a harmonic motion, there is position, velocity, and acceleration are all periodic times. The objective of this lab was to identify the measure key components of harmonic motion such as amplitude, period, and frequency. The materials used for this lab was a spring, set of masses, motion sensor, computer with graphing software, and last but not least, a stand support system. The procedure for this lab was by initiating an attachment to a mass that would stretch the spring about 50% of its initial length. Then, this would allow the system to reach equilibrium, which is said to be the rest position. Then, we will set the motion sensors at the 0 point, and then we will add the 3 graphs that we were to required, which was the position versus time graph. The next one was the velocity versus time graph, and last but not least, the acceleration versus time graph. Then, we will put the mass upward near its original spring length, so now without the 50% that we did before, and then we will release the mass to start the oscillation. We will record for the motion for at least 3 complete cycles, and then we will stop the recording. We will have to repeat these trials if needed, as sometimes the recorded data was to be inaccurate. So for the data analysis, with each graph that we got, we identified the amplitude, period, and frequency. The period was measured by taking the time differences between 2 identical points in one complete cycle. For example, in the position graph, we used 0.9 seconds minus 0.3 seconds, which gave us a period of 0.6 seconds. Then we use the relationship between frequency and period, which is F equals 1 over T. Substituting the period of 0.6 seconds, we got the theoretical frequency of about 1.6 Hz. The experimental frequency measured from the graph was 1.5 Hz. To compare them, we used the percent error formula. Our percent error was about 10%, which shows that the experimental data was close to the theoretical relationships. We repeated the same process for the velocities and acceleration graphs. Even though the graphs are shifted relative to one another, they all had approximately the same period because they describe the same harmonic motion. For this lab, we experienced various challenges such as the equipment issues, the computer and the sensor setup. Once again, we had issues with the computer, so we had to collaborate with another team. The sensor setup was a little bit tricky because if it wasn't set up correctly, it wouldn't record at all, it would record it all messy and stuff like that. Then we also had difficulties on getting clean graph data due to the sensor, as I said before. The motion speed also affected the sensor accuracy because too fast caused high peaks and little waves. Then we had some issues in the small inconsistency in the trials because it was hard to get the right motion as needed. Overall, throughout this lab, we concluded that this setup of this lab allowed the system to demonstrate a simple harmonic motion. It also allowed the period to remain consistent across all the graphs. The frequency matched the relationship of the formula of F equals 1/t with such a small error. Minor errors came from the sensor accuracy, inconsistency of the release, and the data collection timing. The people that participated in this lab was Sileme Rivero, who helped in the video editing, lab calculations, and the audio, Danitza Canales, who assisted with the recording and the video content, Diego Padilla assisted during the lab, Angela Aguirre assisted during the lab, and Annika Wagner, who assisted during their lab as well.